So after seeing the application, or you can say how to find equivalent Thevenin and Norton theorem, let us see how superposition theorem is applied for AC circuit. So it is same as done in DC circuit. So here we will move with the example for superposition theorem. If you see, these are two sources here. One is a voltage source, and other one is the current source. So 10 angle 30. So now on we talk about AC circuit in phasor domain itself, ready-made. So here it is 10 angle 30 ohms, 30 volts, and this is 20 angle 0 current source. And the idea here is that we have to find the value of I0, and this I0 will be found using superposition theorem. So what we mean here is with one source at a time, taken at a time, we'll find I0, and then we will combine them to find total I0. So I0 dash is taken when only voltage source is present, and I0 double dash or 2 dash is taken when only this 2 ampere source is there in the circuit. So let us go to find I0 dash here. So here when you remove this source, you see this comes out to be open circuit. So this is open when you remove a current source. So zeroing out a current source means keeping the circuit open. And this is the equivalent circuit which you get once you have only this source. And this is I0. So to match with I0 dash, I have taken I1 in the same direction. So I1 is basically I0 dash also, and this is I2. And we can write the equations for I1 and I2 and find the values of I1 and I2 using that mesh equations. So here for mesh 1, that is I1, this is what we have, 8 plus J2 into I1. Okay, 8 plus J2 into I1 minus 4 times I2. I think there is a mistake here. 8 minus J2 minus I2 is, I think there is something I'm not getting. What is the problem here? There's I'll write the equations myself. Let's erase it. So if I start from here, so minus J2 ohm into I1, always a drop. So there will be a minus here, minus 8 ohm I1 minus J4 I1 minus I2. This should be the equation, I feel. Let me check if it comes out to be same. So this is J2 I1. So 8 plus J2 I1, and this is J4 is also here, I1, so J2 and minus J4 I1 plus J4 I2. So J4 can be added here, so 8 minus J2, 8 minus J2. So this is done, and plus J4 I2 equal to 0. So this is for mesh equation 1, which actually matches here. I think I could not get it at first sight, so I think this is same, equal to 0. So the difference is only here, it is I1 is here, so that is okay. I1 is here plus J4 2. Okay, so you can always I think there is a small 8 plus J2 minus minus J4 minus okay, it was minus here, should have been minus here, okay, minus, okay, so it is same equation here, but I could not get it at first glance, therefore I wrote it once again. So it is same equation, and hopefully second also would be correct. And you can try out the second equation, that is 10 angle 30 minus I2 into 6 ohms minus I2 minus I1 into J4. So by that way, this is, I think, maybe simplified one. So, or better I'll write it so that this is clear. Two equations. The first equation is okay. Second equation, mesh 2, according to, I get 10 angle 30 minus I2 into 6 ohms minus I2 minus I1 into J4 equal to 0, and I think that should match. 10 angle 30 minus I2 into 6 minus I2 into J4 minus I1 plus I1 into J4. So here I2 6, so 10 angle 30 minus 6 plus J4 I2 plus I1 into J4, and I think this is exactly the same equation. This and these are same except for some manipulation in signs. So that is how this is for mesh 1 and mesh 2, and once you write this equation, you can solve them for I1 and I2. So I1 is required here, so I1 and I0 dash are same. So this is the first part of the current. Similarly, you can find the second part. Second part is when you remove the voltage source which was here, so there is a short circuit here, and for this you can again find the currents. So here you can find the current. If you can write the, here I think they have we have used, I think, some kind of series parallel combination to get the because these two are in parallel, so you can put this in parallel here, so you get 2 angle 0 and 6 and 4 in parallel. So this point is in parallel to this, so this is here 6 and 4 in parallel, 6 plus J4 in parallel, and the other one is the other part, which is 8 minus J2 here. So this is basically now a voltage current division circuit, and you can find I0 by using this formula. So it is a simpler circuit, so we are going this way. Or if you want to make it more complex, you can always make nodes or meshes and do it. So this is what you get. I0 here, again of course a phasor quantity, and then you can calculate value of I0 as I0 dash and I0 double dash, add them, and you get this as the phasor quantity. So now here the answer is acceptable in phasor itself because the question was already in phasor domain. If the question is given in time domain, then one should convert it into time domain, but if it is given in phasor domain, you can just put as it is. So this is for superposition theorem. Now one of the important theorem for AC circuits is called maximum power transfer theorem for AC circuits. We have already seen this theorem in DC circuits, where we found that these two resistances, load resistance and source resistances, should be same to have maximum power transfer from the source to the load. Here we are taking now AC circuit, so this is VTH, or you can say a voltage here, and this is the source, or you can say Thevenin equivalent. So Thevenin equivalent is basically a source, practical source. So this is VTH and ZTH, and this is basically the load here, and load is also impedance RL plus JXL. The idea is to find out the condition in which maximum power transfer takes place from the source to the load. So here we can calculate the value of I, which is quite simple. It is basically a series circuit, VTH upon these are all AC, so it is actually a phasor. So I is a phasor now, and this I can be calculated like this. And once you have this I, now you are putting it as a real part and imaginary part and VTH here, and now I can find the power here, that is I is known, so I can find I square R. So I can just square it and put R to that, multiply R with that. So that is what is done over here. It has been squared, and since this is, you have to remember that this is impedance, so it is basically complex number. So when you square it, it comes out like this, VTH square into RL, and this is the power loss in the circuit. So if you see, this power loss is quite very clear from this. It is basically the total power loss, that is, or the power delivered to the load, that is dissipation in the load, is I square RL. And if you see, this is actually a real quantity. Now, when this will be maximum? So if you want to find this to be maximum, you have to see what is the value of PL, how PL changes with RL, assuming that ZL, that is the load impedance here, is adjustable. So I can adjust it to get the value, a maximum power transfer. So you can find del PL upon RL equal to 0. That's that you have to equate. And also XL can be, X load can be changed to del PL upon del XL. This too should be put to 0. And since there are two variable XL and RL, you need two equations to find the maximum to get the value of PL, to get the two variables which maximizes PL. So if you do that, you will find that this equation comes into picture. That is, this part should be equal to 0, okay, and RL plus RTH, and this part should be equal to 0. So if you differentiate it and see, you will find that this happens, and that gives you that XL should be equal to minus XTH. This is possible because in AC circuits you can get impedances negative, reactance is negative. So here it means that if it is XTH is inductor, then XL is going to be a capacitor, so that they cancel each other. And here when you put this XL, you get this one, and again you can take derivative of this one with respect to RL and equate it to 0. You get RL equal to RTH. So that is how you apply these two equations, and then you can find that that the load impedance for maximum transfer of power should be conjugate of the source impedance. Conjugate means the imaginary part should be negative of XTH. So that is what is happening here, because here it can be cancelled, but RL and RTH are equal. So that is how maximum power transfer happens in case of a AC circuit. Here let us go for example, small example to complete this particular topic. Here we have a circuit and we need to find the value of ZL for which maximum power can be transferred from circuit A, this is circuit A, to circuit B. So B is basically ZL and I have to find the value of ZL so that maximum power is transferred from A to B. So here we have to first find the equivalent circuit, Thevenin equivalent circuit, and then according to Thevenin equivalent circuit we can find, once we know ZTH, we can find ZL, which should be actually conjugate of ZTH. That is as simple as that. So here we are first finding out the equivalent ZTH, because we are talking about only here about ZL only, what will be the maximum value impedance here. So seen from here, first we can find ZTH, and ZTH, that means we will zero out the voltages. So voltage here is, source is short circuited, and now you can find the value of ZTH, and that comes out to be 2 ohm. Okay, so basically these two are in parallel. 4J and 4 ohm, and minus 2J would be series to that. That is what is done. So you can calculate yourself for seeing the correctness. I feel it is okay. It is coming out to be 2 ohm, and by that you will find ZL equal to ZTH. And you can also find Thevenin equivalent. If you want to find the value of current, then you have to find Thevenin equivalent. So Thevenin equivalent is basically the voltage across this 4 ohm resistor, and it is simply a voltage divider circuit, and that is what is done here. So it is a voltage divider circuit having with a 40 ohm volts, 40 volt source, and that is what you get as VTH. And from that VTH you can calculate the value of maximum power using the formula which was given earlier. Here it is quite simple because you are having RTH here, so you can easily find out the value to be 101. So we'll stop here, and this completes the various methods applied for AC sources for analyzing, and we saw that they are quite similar and in a similar way as in case of DC circuits, except for the fact that they are phasors here. So that was the idea of doing AC circuit.